In this webinar, we'll take a look at some of our most useful and commonly used analytical test methods and techniques. I'm Annie Wilt, and I've been an analytical scientist at Sterling for nearly 3 years. And I've got analytical method development and validation experience across the phases of pharmaceutical production and development, as well as in the biotechnology and textile industries.
My name is Katlyn Jelosek, and I'm an analytical scientist here at Sterling. The primary focus of my role at Sterling is method development for APIs. I've been developing methods for semiconductor materials and small molecule APIs for over 6 years.
Today we will discuss high-performance liquid chromatography, gas chromatography, and mass spectrometry.
We'll also take a look at Fourier-transform infrared spectroscopy and other physical measurements. High-performance liquid chromatography, or HPLC, is an analytical technique that is the bread and butter of most API analysis, and is used for evaluating and determining potency, purity, assay, amounts of API versus other materials, reaction completion, and even isomers or enantiomer separations. This technique uses a liquid mobile phase and solid stationary phase to selectively separate the API from intermediates and impurities based on the component's relative attraction to the stationary or mobile phase. The sample is injected as a liquid, either having been diluted with a compatible diluent or as a neat sample, into the system and to then be introduced to the liquid mobile phase, which carries the sample to a stationary column. A detector, of which there are several varieties, then measures the different responses as it passes through and plots the signal onto a chromatogram, showing area of the resulting peaks versus time. We can utilize different types of analytical columns or different solvents to modify the retention of compounds in the system and encourage separation and good peak shape. There are a myriad of different types of columns, short-chain hydrocarbons, phenyl groups, or different cross-linked compounds that allow us to tailor our methods to the compound of interest.
Similarly, there are numerous detectors that we can use to evaluate different types of compounds. Most often used at Sterling are diode array, or DAD, and ultraviolet detectors. These are utilized with compounds that have a chromophore and work by passing light of different wavelengths through the sample. The energy from the interaction of the sample with the light, e.g. pi to pi star transitions, in response to the different wavelengths of light being passed through the sample is measured. We can evaluate a specific wavelength or look at the compound result over a whole spectrum. DAD detectors are also very useful for evaluating peak purity during force degradation and stability studies, because it can prove that there are no compounds co-eluting with the main product across a wide spectrum of wavelengths. Evaporative light scattering detector, or ELSD, are useful for compounds with poor UV response or those that lack a chromophore. These work by nebulizing a sample solution across a light source. The scattering of the light or disruption from the compound is measured and compared to the non-scattered light to calculate the compound response. Charged aerosol detection, or CAD, is similar to ELSD, but an electrical charge is applied to ionize the analyte. The resulting change in energy is then collected by a detector. Refractive index detectors, or RIDs, detect the differences between the refractive index of a solution with a sample in it and the flowing mobile phase. This is another detection method that is useful for compounds with poor UV activity, but they do have a fairly low sensitivity, so it's a trade-off to consider with a universal detector. There are numerous other detection methods, but these are some of the ones we use most commonly at Sterling. With regards to calculating the potency of a compound, chromatography is used primarily as a means of quantitation of compounds and confirmation of identity. We'll compare the peak response of a sample of unknown concentration to a prepared standard or other internal metric to calculate the solution concentration. This value is used in tandem with a percent area purity value and any other supplemental data such as water, solvent, or inorganic content to calculate the overall potency of an API. Chromatography is also a good method for confirming the identity of a compound based on comparisons to the retention time or spectra of a standard.
Another type of chromatography is gas chromatography. It is quite similar to HPLC. In this case, the mobile phase carrying your sample through a stationary phase column is an inert gas, usually nitrogen or helium, instead of a liquid. After your sample has been dissolved into a diluent, the GC will volatilize your sample into the gas form, either using a headspace preparation or in the inlet of the GC. The sample is carried onto the column by the gas, and a temperature gradient, along with the affinities for the stationary phase, pushes the sample through the column. This technique is mostly used for residual solvent analysis, but can also be used for impurities that aren't usually detectable on HPLC detectors. The method is also used to determine the purity of solvents used as raw materials in GMP production and are released using GC methods.
There are different types of detectors in gas chromatography. The most common detector used in our lab is the flame ionization detector, or FID. This uses the hydrogen flame to ionize the organic compounds, solvents, APIs, etc. The ionized analytes are then measured and the signal is plotted. A thermal conductivity detector, or TCD, is an alternative detector for samples that would not work well with FID detectors or are difficult to ionize. These are used for siloxanes and light hydrocarbons and can have operating temperatures of 400 degrees C. Electron capture detection, or ECD, is usually used for measuring the electronegative compounds from an inert gas, determining the amount of halogenated or organic metallic compounds, and it usually uses nitrogen as a carrier gas. GC is a very versatile method that can be customized for efficiency to quickly and accurately measure the solvents used throughout the synthesis of pharmaceutical batches, as well as the purity of samples that can't otherwise be analyzed by HPLC. Mass spectrometry is an incredibly powerful technique that allows for the identification and characterization of compounds, both known and unknown, especially when used in tandem with chromatographic methods like LC or GC. Chromatography on its own only separates mixtures and aids in the quantitation of compounds. Mass spec can provide structural and spectral information that enables the identification of compounds and provides details to the structure of unknowns. Typically, a sample is introduced to an ion source, which causes the material to become charged, either positively or negatively, depending on the source and what works best in the analyte, or it breaks up into charged fragments. Both of our commonly used LC-MS ion source types work by aerosolizing solutions and evaporating the surrounding solution to form bare ions from the compounds of interest. In electrospray ionization, the sample solution is pushed through a small charged capillary. As the solution is charged, and like charges repel one another, the solution is forced into an aerosol mist. A surrounding stream of gases will nebulize the liquid and drive off the sample diluent. As the solvent evaporates, the sample ions are driven closer together and directed into an ion transfer tube and lens structure. The ions observed are created by the addition or removal of a proton or other common adduct. It's also possible to observe multiple charge states, especially in large molecules. Atmospheric pressure chemical ionization, or APCI, is a slightly harsher ionization method than ESI and may result in higher fractionation of the analyte of interest. A solvent spray is heated to a high temperature and injected into a nitrogen stream. The entire resulting aerosol cloud is passed over a corona discharge needle that generates ions as the solvent evaporates. However they're generated, the ions are then separated according to their mass-to-charge ratio. This is done by accelerating the ions and subjecting them to an electronic or magnetic field to direct the ions into the detector. This is often done using a quadrupole, which utilizes different magnetic frequencies to direct, manipulate, and deflect the ion beam towards a detector. The detected ions can then be plotted against time to give a spectra of all ions detected. Ions with different mass-to-charge ratios will be deflected differently in the detector and can be filtered out by mass of interest. This can be used to select a specific mass, i.e. from the analyte of interest, for further fragmentation. The selected ions are then subjected to another round of collision and ionization before being sent through another separation mechanism such as a quadrupole or time-of-flight detector, which can quantify the different masses and fragments detected. This can be useful in separating the target compound from a complex matrix by selectively scanning for the mass-to-charge of interest and sending the rest of the sample to waste. The mass-to-charge ratios observed can also provide structural information, especially since compounds often break apart in predictable ways. Compound libraries can be utilized to compare the fragmentation pattern of an unknown compound to thousands of studied compounds to give an idea of what the material might be, or isolated impurities can be compared against the spectra of known APIs to determine if they are potentially related or degradant products. LC-MS or GC-MS are exceptionally useful tools because they allow data to be generated that is both quantitative and qualitative. Traditional chromatographic methods only serve to quantify the purity or quantity of a known compound and do not provide much information about the compound's structure or identity. We can make reasonable guesses on the compound behavior in a chromatographic system, but mass spec allows us to definitively know what we're working with as well as its quantity. It's also incredibly sensitive. It can be used to evaluate analytes that have a poor UV response or not be separated by traditional chromatographic methods, like with peptides and epimers. The slight difference in fragmentation patterns allow us to accurately quantify and identify different structures of the same mass.
Fourier-transform infrared spectroscopy, or FTIR, uses infrared light to change the dipole moments of the molecule in question. This causes vibrations of the molecule. Each functional group within the analyte has a distinct vibrational energy. This is then measured by the detector and plotted by wave numbers of light, and that shows which functional groups make up the sample. We typically use this method to identify compounds, usually against a standard for confirmation, though you can use this technique to build an unknown. This technique is also desirable if there isn't a lot of sample available, as you only need a few milligrams, and it is not destructive, so if you need to reuse your sample, you could. The newer units for FTIRs are also quite small and only need a laptop to accompany them, an easy benchtop technique. Sample analysis is also quite quick. Turnaround times vary depending on your method, but usually do not take more than a few minutes.
Other physical testing methods and techniques are used to evaluate inorganic compounds, remaining volatile material, or water content. Residue on ignition testing, or ROI, provides a measure of the quantity of inorganic material in a sample by burning off any carbon-based or organic material through both sulfuric acid and heat charring. This result provides another component to the purity-potency equation by giving an accurate quantitation of inorganic material that may not be detected by other testing. ROI testing provides the quantity of inorganic material, but does not give an indication of what the material might be. For that, we'd need to turn to elemental analysis or ion chromatography.
Karl Fischer, or KF, is a technique used to measure the amount of water in a sample. There are a couple of different measurement techniques for KF. Volumetric KF, or VKF, is based upon the reaction of sulfur dioxide upon iodine, titrated into the KF vessel, and dissolved in pyridine and methanol. The resulting measurement of iodine is equivalent to the amount of water in the sample. The detector measures the resulting reaction for iodine as a percentage of the amount added. This technique is usually used for higher percentages of water, usually greater than 1%. Coulometric KF is another technique, also known as CKF. This measures very low levels of water in the sample. This method is similar in that the measured iodine is equivalent to the amount of water, but more chemical reactions are taking place to get to the same result. This method is much more sensitive and allows for lower detection limits of water, as it uses an electrochemical endpoint for its determination. Loss on drying, or LOD testing, is a measurement of any moisture or volatile compounds in a sample, and is performed by drying a sample in an oven, either under vacuum or atmospheric pressure, and measuring the difference in the weight of the sample before and after drying. This value only covers how much has been lost upon drying and does not provide qualitative information, but it's a piece of the overall potency calculation.
There are countless different testing methods, and all provide different pieces of the puzzle when it comes to the characterization of an API or other compound. By focusing on what is most of interest or concern with a product, we can tailor our testing plan to ensure that we collect the most important information.
I'm Katlyn Jelosek.
And I'm Annie Wilt. Thank you for joining us today for this look into our approach to analytical method development at Sterling.